I'm going today. You guys come by bus? Nagida and Puza?
Yeah, not together.
So how frequent is the bus?
Every 30 minutes.
Every day. Not bad. Oh, the quiz. All of you got it mostly right. So you guys all know whatever I'm going to be teaching today.
I was a little unsure if that was,
Sounds what?
I was a little unsure if that was the correct, right?
Okay. You'll make it. Maybe,
Right.
maybe you'll
But
grow more
doing it
confident.
made more sense.
Okay. The right place. No. Homework 2 is over, I guess. Homework 3. Then is homework 3. Homework 2 is due next Tuesday. Yeah, but it's next Tuesday, so we had 6. Homework 2. 2, yeah. Oh, yeah, homework 3 is not posted. It's only 4th week. It's still on homework 3. You guys owe me extra classes, right? But sometime we should use it.
Yeah. Sure things.
I think we lost a lot of classes. Maybe we should do that. Not now. Not this week. Or shall we? The only point is that the week I do the first extra class, the homework calendar idea is to if on Tuesday I have a class and Tuesday evening I have a class and the homework is due on Thursday. I don't know how to do this. Yeah, we'll find a way. This week seems a reasonable time to do it because I think contents have been covered for this. At least today I'll be covering it. The next ones can be done. But it all comes at a price. I often feel that it is better to go slow in the beginning because then it's time for you guys to seep in. It's not just about finishing the curriculum. So functional derivative seems to be new, so I'm going to give it a, let's go a little slow. Even though in principle I can speed it up. Let's see, we will wait and see how things go. Yeah. Somewhere around spring break might be the time when I can put in, not during the spring break, before the spring break. I can speed up maybe one lap on Friday or Thursday of that week. You can put in one lecture there. But something that we'll think about. Yes. Okay. We have been doing functional derivative and There's the quiz. Yeah, sorry for asking. I'm asking because I noticed that most of you guys did it correctly. Assuming that you understood the steps, then that's pretty much what I'm teaching today. No, let's discuss this. Yeah. So we want to have an idea of functional derivative. Let's think of a few things. So first is derivative, let's say one variable derivative, if I would call that. I think it can be called one variable derivative. Not sure technically what it's called, one variable derivative. This is the standard derivative that we study for the first time when we are doing calculus. Let's say there is a function, a variable x. The function is f of x, and you would say x is equal to, you would define this as limit delta x tends to 0, f of x plus delta x minus of f of x divided by delta x, like we should all know what that means. Quiz, right? Let's see. Take f of x to be x cubed and find derivative of f of x. We know that is 3x squared, that is what I'm asking is to prove that. Okay, prove that the derivative of this is 3x squared. Okay, that requires using this idea. Like make a small variation, do a series expansion, and then subtract out, and that brings out the idea that is 3. That's called derivative by ab initio. That's how Newton did it. Most of what Newton is popular for his contributions to calculus is that making it a rigorous proof. If you are doing multivariable derivative, and then you say it is a function f which depends on y1, y2, and so on. It often you say is f of yi, so there is yi is the variables now. Variables, like it's plural, there are many variables, and the function is there is of course a derivative with respect to each of the variable, but the significant or the using this, there is one more identity you use, and first let me say this particular identity, so that's derivative of f with respect to yi would be equal to limit delta yi tends to 0, therefore y plus delta yi minus f of y divided by delta y. Notice this is for each I, right? For each I. So there are multivariables, so you can have a derivative with each of those yi, and then you are, that's not sufficient in the sense that you have to put in one more condition there. that each of these variables are independent of each other, right? That's a condition we put, and that is given by yj over yi. That's equal to delta of ij. So this is and. So there are two conditions in multivariable calculus, that what is the change in this due to a small variation in y. And you have to show that each of these variables are independent of each other. When I'm taking the derivative with x, I keep y, I pretend y is a constant, like we all do this in partial derivative. When I'm taking the derivative of z, I pretend x and y are constant. That's what this states. This is a Kronecker delta. We introduced this last time. Now we are extending this to a continuous variable, which makes this practically, if this is, this could also be infinite variables, but instead of discrete, now we are saying it is a continuous variable. And the third thing is, this is what we are working with, and that's functional derivative. So you would say this is f is a function of functional of y, so that's a functional of y. That means y is a function now. Y here was had an index I. Here it is a function, and y of x is a function, if you want, and f of y is a functional. Functional practically means that you can have, the function is not specified. Y could be any function, right? I don't give you which function y is. Like when I do a function of x, we say x is a variable, right? I don't know what x is. For a given x, I'll give you a f. Here we are saying for a given function, I'll give you a functional. So function is the input. Give me all type of functions, tangent, sine, cosine. I don't specify anything. Give me any type of functions, and we can think of it as a function. Okay, so the input is a function. So it's a much broader terminology in that sense. And now you say that for each x, instead of for each I, you have, so you change the, so this was a total derivative, then you became a partial derivative, and this is called a variation in f. F is sufficient, but I'm just completing it with respect to y at point x, right? So for any I can make a variation for any x. So think of it, so I'll draw this and show this in a minute, and you would again say this is limit. In this case, it is delta y. So delta y tends to 0, f of y plus delta y. You make a small change in the function now, minus f of y itself divided by delta y with respect to x. And I need to put in an additional condition that these variations are independent of each other. So the variation in y at x is independent of the variation of y with respect to x prime. When it is discrete, you say it is a Kronecker delta. Now it is a continuous variable, so it is x minus x prime. And you have to introduce all the properties of a delta function. The primary idea is that it is 0 everywhere except when I is equal to j. This is 0 everywhere except when x is equal to x prime. But I also need to capture the fact that it is, when I do an integration, I capture that one. And the only possibility is that this has to be infinity in that case. And you also need to have the recall, right? So recall that integral of dx delta of x minus x prime is equal to 1. If you go in a region where X prime is captured, that's equal to 1. So that's the same idea as here. That's the quantity you need, and most importantly, you need this. As a practical user, we want to use this, and you want to have the meaning associated with it. Variation in Y with respect to X is independent of variation of Y with respect to X prime. So let's have a couple of examples. Let's have, we were talking about Fermat's theorem. This could be X is deciding which region, like when light is going through there, the medium it is going through, and N of X is the refractive index in the medium. So at every X, there is a refractive index, and it is layered medium, and the trajectory of light, so Y of X is trajectory of light. And when you want to find the trajectory of the light, you start from an initial point and go to a final point. Right? And Fermat's theorem tells us that think of any function that you can go from here to there. This could be Carbondale, that could be St. Louis, and think of all possible routes that take you there. Right? You can take 2764, the various ways, and then you ask which route gives you the minimum time. And that's what it will be, that's what the system will select. That's the Fermat theorem. But what we are asking is that give me all possible trajectory. That means all possible functions, right? All possible functions, right? This is a function, that's a function, that's a function. And out of all that, there is one particular piece which is picked by the system. What is all possible functions? That's a functional, right? Out of all possible functions, I want to find the minimum. It's a function. So that's important. I'm not thinking of a variable now. Variable is a point. Now I'm varying the function itself. So that variation, if this is the function of interest, right? We don't know that answer yet. And if I'm making a variation, let's say this is a variation at X, and that's a variation in X prime. Is that clear what I mean? So that's your Y of X. So let's say that's Y of X, that's Y of X. I don't have to write that. When I am saying it is being changed, the variation is between Y of X and the change. Right? This variation is independent of each other. Like think of a two-dimensional function. I make a change in X, I make a change in Y. They're independent of each other. I don't say that they're anywhere related. They're not correlated at all. That's all we are saying. And in this particular diagram, it will look like this. Why are we doing this? A more interesting problem is that this could be time now, and this could be the trajectory of a particle thrown up in the air. Right? When I throw a ball up in the air, I know that it's a parabolic trajectory. That's what Newton's law tells me. Like Newton's law tells me that it will be a parabola, like with respect to time, not with respect to X. It will be with respect to time. It will be parabolic, but that's Newton's law. That is assuming Newton's law. But Lagrangian or action principle will say that start from time t1. So this is time t1, and go to time t2. Let's say that's your initial value x1, and that's your x2. And throw a ball and reaches a certain height x2, x1 to x2. And we are saying, what is the trajectory with respect to time? Does it go slow down? Does it speed up? That's what we are saying. And its trajectory will look like this. Like that's a parabola, presuming, let's say, that's parabola will look something like this. So that's a parabola. That I know the answer, right? That's Newton's law. If I accept Newton's law, that's what it is. Action principle will say that give me all possible trajectory. That's one trajectory, that's second trajectory, that's a third trajectory, and it doesn't even have to be all nicely distributed. This could also be a trajectory. Right? Give me all possible functions. That's what we're saying. Give me all possible functions, and the one that will take the minimum, or not the time, it is the action. The one that is having a minimum action, value for that action, that's what the system will take. So system somehow has a feel for action, right? Action is integral with respect to time of the Lagrangian. We will introduce that later. That's what we are talking about. And here, I want you to appreciate this fact. Now it is a x as a function of time. So if you have this as t, so that's your x of t. And this is the variation, right? If I say these are the trajectories, so that's my change in x at time t. The change in x at time t prime, that's t prime, these are independent. These two variations, by definition, I'm saying it is independent, exactly like here. I'm saying x and y, when we do partial derivatives, are independent of each other. We say that the variation in t that we are making to get the Newton's law is independent. And that will be stated in this form. So this boxed equation is what we will use as a practice. That's the concept. So let's start using examples, and hopefully as a user, it's exactly like a derivative. First time when you're doing derivative, it is possible to escape the depth of the definition of a derivative and still do all the problems, because we are mostly mechanically doing. If you know if you remember the fact that x cubed is 3x squared, x raised to n is n times x raised to n minus 1, you can do all the problems, at least in an exam that calculus 1 course gives. Similarly, most of the problems we do as a user level, there is some tricks you want to learn, which will take you through, even if you're not very comfortable with the concepts that I tried to illustrate here. But that doesn't mean that you should avoid it. You should try to think both ways, but do it in a balance. Okay. Okay, so the first example we did was, let's say f of let's say u, right? It's equal to integral infinity to plus infinity dx a of x and u of x. And the understanding is that a of x here is a given function, and it is a well-defined function. Whenever you say well-defined function in an applied course like physics, like pure mathematics is different. If you're doing this at a fundamental level, then you question what that a nice function is. Here, the nice function means that it'll go to 0 at infinity. That's mostly what we're saying. And in between, it doesn't have any undesired features like it going to infinity, right? Everything is finite. That's what we mean by nice function. There might be more features on that, so we want to, everything is, all the definitions doesn't get hurt. There is no an exceptional case in that. That's what we're saying. We want to do the functional derivative of this with respect to u at, let's say, I've already used x here, so I should use another variable, so let's say x prime. If they are asking you x, then you want to change this, right? Make this x prime. You cannot use both, that's a dummy variable. So either you change this or that. So one of them you want to use. And first thing I'm going to do is just as a practical how you would attempt on this. I have to operate this. I'll do it in few steps, but very quickly you will realize that you can jump these steps. That's minus infinity to plus infinity dx a of x u of x. Is that clear? So that's what this means. You're operating this with respect to this. Notice this is an x prime dependence. This is an integral and dx or x. So this can go through. Only when there is an x prime integral it cannot. So it will go through here. U of x will hit u, right? This is a derivative with u. So this will care for this function u. So it can go all the way till there. This function doesn't care for. So this is minus infinity to plus infinity dx a of x. And now you have the u x over u x prime. And then you say that, oh, this I recognize, this is a variation in u at the point x with respect to the variation in u at point x prime, and we said that they are independent variation. So that's a delta function. So that's delta function, that's minus infinity to plus infinity x a of x times a delta function. And I know how to use a delta function. Whenever there is a delta function integral, replace the function with x prime and you're done. So that's a of x prime. That's the functional derivative of this integral with respect to u. Notice you could have been anything, and I'm just saying this is the way with respect to all possible functions, that variation gives you a. That's that idea. Okay, that's how we will be using this definition. Yes, Kushal.
Why we don't like if we got the AX and directly go to the.
Because we are making a change in the u, right, not a. So let me clarify. So as I said, this is the simple, this is a shortcut. Let's do the long way. Long way will involve this, right? This is if I tell you what is the derivative of x cubed, you immediately say 3x squared. But that's using a prescription. Someone told you in a textbook that's 3x squared, but whenever you're in doubt, if you forget this sometime and then you want to derive it, you're stuck in an island, you don't have a book, then you would do this, like presuming that you know how to work this. So let's use this principle and work this out. So I'm going to do the same thing and use the ab initio principles and try to derive this. Most of the time when you're doing your homework or when we are doing in this course, this is good enough. You don't even have to do this, you don't have to write this step, you can write this and immediately write this here. If you get fast enough, like often you'll see that, oh, you get used to this, right? So you can immediately do that, right? The idea is to find this, and this will itself get complicated. This won't be, this is the simplest functional you can think of. So let's do this. So for the fy with respect to y of x or variation in x prime is equal to limit delta y tends to 0 of f of y plus delta y minus of f of y variation with respect to y. Right, so let's make it more specific. This is x prime. That involves finding what is y plus delta y. And this raises a question. I think Manuka, it was you again who asked. This variation is x dependent. Right? At every x, I have a variation, right? At every x, I make a change in the function. So that's a variation and that. So let's do that. So that's the same as dx a of x minus infinity to plus infinity. Wherever I see a y, I have to introduce a variation now. So that's y of x plus delta y of x. I made a change here. This could be any function, right? Any function, that's the change I have made. Now, let me subtract this out. Y plus delta y minus of f of y is equal to f of y is nothing but this first term in this. Right, when I expand this out, that's f of y. Let me write this down, maybe it will come. E of x, a of x, y of x plus minus infinity plus infinity x a of x delta y of x and minus of x a of x y of x. And this will cancel out. Always, that's a property of a derivative. Whenever you do this, for example, if you were doing this function for x cube, the first term will always cancel out. That's a feature that always works through. That's a numerator here. So delta of f of y with respect to x prime now is equal to limit delta y delta y tends to 0. This is x prime if you want. And this is 1 over delta y prime. And then this is the integral, that is a plus p of x, k of x, delta y of x. It might be good to say that this is delta y instead of this small delta. That's also perfectly fine. That's just saying that we are differentiating between the two. Technically, unless I don't clarify that, that's not important. So that's it. Like usually the understanding is that, at least in my notation, it depends on the textbook, that when I write delta, it is not infinitesimal. This is infinitesimal. This is infinitesimal. But when I say delta x, it could be large. Right? You're taking the limit delta x tends to 0 is what dx is. That's I have that in my mind, but unless I specify that in very clearly in notes or something, it's not important. So now at this point, this is x dependence. I can take this inside. So that's equal to d of dx minus infinity to plus infinity x, and limit delta y x prime going to 0 of delta y x over delta y x prime. This is the idea of a delta function. This is how you take the limit and say that that's equal to a delta function. That's delta function, and now we have reached the same step there. Minus infinity plus infinity dx a of x times delta of x minus x prime, and that's equal to a of x prime. At this point, the question one of you had was, why don't we worry about a of x? Here you see that making a variation in y, right? A is a fixed function. A could be, for example, tangent theta. That's a given function. Think of a problem again here. This is given. Refractive index is like a of x. That's given to me. The trajectory of light is the unknown, right? Y is the trajectory of light, and a of x is some known function. I'm not changing a of x. It's a y that I'm changing, right? That's a parameter in the problem. And you can do that. But again, this is I expect you guys to know this, but as a practice, this is what you need. Like, for example, I specifically can ask you what this is. But if I don't mention that prove this, then the understanding is that you can use this. You can use the shortest way possible. If you memorize it, that's perfectly fine. But the idea is that you should be able to do the derivative. But at any time I can come and say that, no, prove this. Then you should be able to do this. So most of the time I will be depending on that. Okay, clear? So let's do more examples. Any question here? Can I erase this? Right?
Yeah.
So,
Yeah.
okay. So let's do u of x cube, right? That's a simple thing you can do. And again, you would do. So now notice how I'm going to work at this point. Have this in mind that f of g of x, right? This is a chain rule, right? If I'm doing a normal derivative, d of x with respect to x is the same as d of f with respect to g and g of x, right? That's chain rule, right? That's what you say, it's a chain rule. This is for normal one-dimensional, one variable calculus, right? But this is a similar thing that's going to be there. It is not exactly the chain rule for one variable calculus, but you will notice that the same thing is going to go through. So here, I'm going to do like f of u with respect to delta of u of x prime. So that's the same as this time. I do the first step immediately. A of x is fixed. So variation with of u cube, right? U of x prime. I cannot use the delta function still, but at this point I use chain rule. I pretend, notice what I'm going to do. I pretend that I'm taking the derivative with u. So then it's 3u squared, normal derivative, right? So this is equal to minus infinity to plus infinity dx a of x. I'm saying it is 3 u of x squared. Right? Simple derivative I have done, but that's not complete story. Then I say that I'm going to take the derivative of u, the functional derivative of u, and that's this. So first pretend that you are taking the derivative with respect to u, right? And then at the end say that, oh, that was not really a normal variable, it was a function, so I do the functional derivative. Okay, is that clear? So that's important, capture that technique trick if you want, right? And then at this stage, I realize that, oh, that's delta function. So if you let me do this in 2 steps. You can at this stage write the answer if you can see through, but u of x squared and delta of x minus x prime. That's equal to a of x prime now. U of x, no, 3, right? Or 3. Doesn't matter where you put the 3. 3 u of x prime squared. That's it. Is that clear what happened? And make sure you realize that I took the derivative of u cube here, right? Pretending I was taking the partial derivative of u, right? That's a trick. If you don't trust this, go back there. Like you will say that, oh, this doesn't make sense. How can this go through, right? Go here, do it explicitly, and you will get the same answer. So you do this 3 times, and you say that, oh, this always works, right? Write a general function, and that's what you should convince yourself. But this is the trick. I'm telling you, you will go through. Okay, clear?
Yeah.
Yeah, we'll
So
do.
the AX3 and UX squared is pretty much the AX that we did before.
Yes, a of x is there before. This is the derivative that. Because, or you can say this is 3 of them, right?
Yeah.
Like another way of doing this is that there is a u, there is a u, there is a u, right? And you're taking the functional derivative with respect to u. Right? You can take the functional derivative with this, or this, or this. So there are 3 terms. Like you can distribute it. Each time you do it, 2 of them survive. And there's a delta function. U squared, u squared, u squared. That's 3u squared. However you do it, convince yourself that it goes through or get the pattern. Let's do a few more examples. Hopefully this will help. So let's say f of u equal minus infinity plus infinity t of x, and I can say a of x plus d of x times u of x, and I can say this is q. All right, just a random function I can put it. Think of derivatives again. If you were teaching derivative to 12th grade students and you have to come up with examples, you will you just put a power there, put a square root, put a tangent, all the known functions you will put in. So I just randomly put some function. Again, you do, if you're doing derivative of f of u with respect to u at x prime. First, we pretend that we're taking the derivative with respect to u. Normal derivative, the classic one variable derivative with u. And how will I do that? That's minus infinity to plus infinity dx. Derivative with u, right? So I will say it is 3 like power, and then a of x plus b of x, u of x square, right? That's the whole thing. And then I will do the argument of this. Like, isn't that how you would do? I mean, there are various, you probably all do it in independent ways.
You would use the chain rule.
Use the chain rule, right? 3 times this, and then the derivative with respect to u. So this doesn't see the derivative with respect to u. And then I will do a b of x. And then the derivative with u itself, which I write as derivative. Is that clear what I did? Right, normal derivative, but at the end, I'm thinking of it as a functional derivative. At the very end of the chain rule where I will do that, that's it. And that's your delta function. Right? If it's a delta function, replace all of this with x prime. And I have 3 times a of x prime plus b of x prime, u of x prime squared, and b x prime. That's it, right? 2 steps. Okay, you want to get efficient with this. Again, you can expand this out and do this in this many steps. I recommend you to do that, but there's nothing wrong in jumping steps. That's perfectly fine, unless I ask you to prove it. If I ask you to prove this using the ab initio principle, then you have to do that. That will be rare, very rare. For our purposes, we want to do this as immediately as possible. Okay, clear? But this is also simple, right? There is only u coming in here. In mechanics, we have the derivative of x coming in, that's a velocity. Then we have acceleration coming in. Here we have been escaping that. This is all simple cases. So like if you remember the case of Fermat's principle, that was the derivative of y that was showing up. So we want to do more examples which has derivatives in it. So let's do the derivative case now. Same, very similar functional, but this time I say I have a du of x with respect to x. That's like velocity. If you think of x as time, then that's velocity, right? If u was position and x was time, that's derivative of x with time, right? So now how do you do this? Again, let's go slow first time, but you will see that it's very similar. So du of x prime now, that will change, that is it's not dummy anymore. And this can go through. It can go through most of it. Everything is x, integral is with x. This doesn't change, and the derivative is x, so it doesn't see through all of x, it can penetrate all of that, and it's here, right? Oops. X, a of x, d by dx, and you immediately reach here. Is that clear what I did? Right, the only difference was that there is a derivative, but this derivative is with respect to x. So I can penetrate this, this is with respect to x prime, it doesn't see it, so it goes through, and that's a delta function. So this is equal to minus infinity to plus infinity dx a of x d by dx, and that's a delta function, x minus x prime. Okay, I know how to do the integral of a delta function, but this is the derivative of a delta function. Now I had wonder, oh, what is that? So the trick to do this also shows up in your homework separately. I do a partial derivative. So this is minus infinity to plus infinity dx d by dx of a of x delta of x minus x prime. Notice now this has become a total derivative. Here at this stage, it was not a total derivative, it was acting only on delta function. But that's not the same. So I have to subtract things out. This is how you would do your what's that called? Integration by parts, that's your integration by parts, probably you think of it as U and V, it's the same idea in here. So now I have to hit the other one. So dA of x by dx. And del share of x minus x prime. This should be easy. This is our delta function now. Now I have isolated my delta function. The derivative is not acting on that. I know how to evaluate that. Any function with respect to delta function, replace the function at x prime. So this one I know. This is easy. I just have to replace this at x prime. So evaluate it at x equal to x prime. You can say e of a x prime over x. This is also easy in the sense that this is a total derivative. So it gets contributions only at the boundary. Right, so think of your d of x, d by dx of f of x. A to b, that's what is that equal to?
F of b minus f.
Very good, right? It gets contributions only at the boundary. Like that's a total derivative. That's a total derivative. So it gets contributions only at the boundary. Christian? No. Okay, so that's equal to A of x. First, you evaluate this at x equal to plus infinity, and then you evaluate this at minus infinity. Presuming that x prime is, so now we are saying that x prime here, I never specified what this is. Let's say this is less than infinity, and this is greater than minus infinity. So most of the physics that we are doing is not on the boundary, so then this doesn't contribute. X equal to x prime never contributes, so both are zero. So this is equal to 0. For almost a month, we will have situations like in all your homework questions, you will see that with variations at boundary to be 0. Like when we are doing this function, I'm not making a change here. Right, at the boundary, I'm keeping it fixed. Right, that's an assumption I made. Then you ask 2 months down the line, is there something else I can learn from this? Like when I don't make the change, I get equations of motion, I get Newton's law, I get Snell's law. So that's what you get. But then you ask, is there some more information in here? What if I really make the change at the boundary also? And this was what Noether is popular for. She did this in 1910 or so. And she was the first one to realize that, oh, even if you change the boundary, there is more information. And you get conservation principles out of it. You might have heard that conservation of energy is related to a very broad statement. Or maybe I should ask you more specifically. Usually conservation principles are related to symmetries. Let's say, think of conservation of angular momentum, right? That's an experiment we do in undergraduate physics.
Observed in a rotation.
Yeah, rotation, yeah, very good, yeah. What would make sure that angular momentum is conserved? What symmetry would you have? I think you almost said it, right?
And
You need spherical symmetry under rotation if your system it remains the same under rotations. For example, think of Earth going around the sun. Think of circular orbit for a moment. It is not, but it still goes through even with elliptic orbit. But for simplicity, let's say it is a circular orbit. You put your axis down here, so that is your Earth down there. And then you ask your interaction, the potential 1 over r square. Does it care for where the angle is? There is no angle in that interaction. 1 over r square is just distance dependent. It doesn't care for the angle, whether I'm looking in this direction or there. Is the Earth in this place or there? So that's a symmetry in the interaction, in the energy, if you want, like you will usually say Hamiltonian later on. If a Hamiltonian has a symmetry, that will imply a conservation principle. So if your Hamiltonian is having rotational symmetry, you get conservation of angular momentum. Like that should be easier to see because usually angular momentum is associated with rotation. What is harder is if I say conservation of energy is associated with what symmetry in the Hamiltonian?
Spherical symmetry.
No, that's angular momentum, conservation of angular momentum, conservation of energy. Ever thought about it?
Hyperbola. Square.
It's a translation in time. That means to say that, let us say. Let me first go back and think of position. It might give you, it is more intuitive. Again, conservation of linear momentum. What is it related to? Can you guess us? Conservation of angular momentum is a symmetry in rotational symmetry. What is conservation of linear momentum?
Straight line.
Straight line, it is translation along a line along X, let us say. So what we are actually saying is that think of this room, like you often say you play a prank, right? You're sleeping and you say that you want to lift the whole bed of your friend who is sleeping and place it somewhere else. And when they wake up, they realize, oh, I'm in a different place. Right? Now do a similar thing. You're in this room, okay? And while all of you guys are sleeping, let us say I shift everything by 1 centimeter. Let's say 1 kilometer. Why not? Right? Everything, the table is moved, chair is moved, the atmosphere is moved, earth is moved, sun is moved, everything is moved by 1 kilometer. And the question is, when you wake up, will you know? That's a symmetry. If you do not know it, if you cannot recognize the difference, that's a symmetry, right? The system has a symmetry you never realize. If you have such a symmetry, that means linear momentum will be conserved. And the same thing is with rotations. Instead of moving this way, I rotate it. I rotate this room, right? But I rotate Earth, I rotate the whole universe for that matter. And the question is, can you do an experiment and sense that rotation? Right? I moved everything. Can you set up so you want to be smarter than the people who are playing the prank on you? You want to design an experiment that, oh, if someone does that, my experiment will tell me that change. And if you cannot design such an experiment, that means that symmetry is there. Right? And then the question is what I was asking earlier, what is energy conservation dependent on? That has to do with time. If I take you from here and place you 100 years in future, right? And then again ask, will you realize that? Like we would always say, oh, our technology has changed and all that, but we are talking about interactions, the whole universe, everything. And if you cannot sense, if you can sense it, for example, technology has changed, that means energy is not conserved. But most often in those cases, we are thinking of local, like we want to think of the whole universe. Right? If you cannot sense it, that means energy is conserved. These are conservation principles and symmetries. Quiz. Read this up and find what's the connection between conservation principles and symmetries. Okay, whatever I listed, there are a few of them, and this is called Noether's theorem. And this is related to what we are going to be doing at the boundary. I said the boundary is kept the same. If I change the boundary, like if this is not 0, it leads to whatever I'm talking about. And we will do this about 4 weeks down the line. We will derive all these things. We will say that if we make a rotation, it implies conservation of angular momentum. If it makes a linear translation, it gives you linear momentum. Time gives you Hamiltonian, or energy is conserved, and so on. That's called Noether's theorem. All that means that this is not 0. Okay. All that to tell you that for us now it is 0. Yes.
Noilers?
Oh, okay, I might be wrong in pronouncing it. Noether's. Noether. She was a German, so she. So. she was the first one to recognize this, and I think she's 1910 or so, like in this about very recent, like, relatively recent. Most of Lagrangians work was 200, 300 years back. This is more recent. So it's kind of impressive. Okay. Any other comments, questions? Okay, all that to point out that we are saying this is zero, no variations at the bottom for now. Whenever I say that specifically, you can put this to zero, that's equal to minus d by dx prime of a of x prime. So you can start from here, you don't have to do this all the time. If you're doing a problem, if you know the fact that derivative of a delta function is always negative of the derivative of the function that you're taking. If it's a second derivative, you will see that it's again plus. If it's a third derivative, it is again minus, and it will change. In your homework, that's one of the first problems that you do about this derivative, so that you can use it again in the later status, right? Is that clear? Okay, but now I can make this more and more. So I can say, I don't have, so first let's do a simple one, right? So we have du x by d of x cube, right? Earlier we did square of a function, now we have a derivative cube of that. That's equal to, so u of x prime is equal to, pretend that you're taking normal derivative. So this is minus infinity to plus infinity dx a of x. I'm pretending that this whole thing is a function of u, so it is 3 times u x square. Right, that should be the easy part, like normal derivative I'm doing. But at the chain rule at the end, I have to now take the functional derivative of this. That I've already done. So this is d by dx of du of x. Is that clear what I did? That's a chain rule if you. This derivative was involved, that I did it slowly. Whenever it's a function of this derivative, that's the last thing I do. But before that, I pretend that I'm doing normal derivative, 3u square. Whatever it is, whatever that whole point is, I just do the normal derivative and then do the normal. I'll do this in 2 steps, but you can jump the step if you are comfortable. It's 3 x of delta function. Whenever it's a derivative of a delta function, I take this whole thing and replace it with x prime and put a derivative in front of it. That's all I have to do. Right? And a negative sign. So this is equal to minus d by dx of a of x 3 du x by dx whole square. But I have to do everything with x prime, so replace x prime, x prime, x prime, x prime. Right. Is that clear? Any questions? When we were doing formats, you know, we had such this expression instead of A, this was N. N is given, decided by the configuration, and there was 1 plus dy. If you recall, that was an expression we got for the trajectory or the time taken for the trajectory of light. Actually, it was not F, it was T, right? And it was C times T, I guess. Because we wanted to get that refractive index. Okay, good. And if I want to minimize this with respect to time, then I make a variation with all possible trajectories. So the variation will be C times variation in T with respect to Y divided by Y of X prime. Correct. And when I do this, I pretend as if I'm doing the normal derivative, right? So this is a little more than just a power. It's a square root, but nevertheless,
Still a power.
still a power, right? So it's 1/2, that's a power of that. I'm doing derivative with y now. Earlier I was taking derivative of u, I'm pretending I'm derivative of v. So this whole thing 1/2 minus 1, this goes in the denominator, right? So 1 plus dy by dx square. And then I have to take the derivative of the argument inside. So that's 2 times dy by dx. So I've still not reached my y, right? Only when I reach y, I have to start thinking of functional derivative. And then I have to take the derivative of y. First the square root, then the power, and then my y functional derivative. At this stage, I say, oh, I have to do the derivative of y, so that's delta y of x, delta y of x prime, and that's a delta function. Oh, I have to be careful there, right? Made a mistake. What's the mistake I made?
Yeah, d over dx.
D by dx, very good. So I do 2 times dy by dx, and it is d by dx is sitting there. Thank you very much. Good observation, very good observation. Right, is that clear? Okay, make sure you realize why I do the d by dx. Okay, because that d by dx was that this was 2 of them, right? I'm taking the derivative, but d by dx of that derivative. Okay, make sure 2 cancels out, that's the innocent one. And since I made that mistake, let me write this again so that there's no confusion. And dy x over dx divided by 1 plus dy x by dx. And this is a derivative of a delta function. But derivative of a delta function is simple at this point, right? I evaluate everything else at x prime and take a derivative of that and put a negative sign in front. Is equal to minus d by dx prime of n of x prime dy of x prime by dx prime. Square root, and this bracket. That's a functional derivative of this whole expression. So if you want, that's Fermat's theorem. Actually, Fermat's theorem is not yet there. This is the time taken for a light to go along any trajectory. if I make a variation, if I set this to 0, that's Fermat's theorem. Right, action principle just tells me that find a variation. If I say stationary action principle, that means I'm setting it to 0, that's a minimum. When you take a derivative, that's normal, but you set the derivative to 0, that means it must be a maximum or minimum.
So no variation?
No, what I meant was, so this is a function, that's a slope, right? So that's derivative. Let me take one variable, right? dy by dx, that's x, y, right? I can take a derivative anywhere I want. That's nothing special, right? But when I say the derivative is 0, that's special. That's either a minimum or a maximum. This is a functional derivative. This is not Fermat's theorem. But the moment I set this to 0, I'm saying the time taken by the light is either a maximum or a minimum. Right? So I have set this to 0, right? So before that, let's recognize something here. This numerator, if I were, so this quantity in here, remember a trajectory. And if you make a small, this is dx, that's your dy, and infinitesimally, this is ds. Right. If I do sine function here, so that's your angle theta, I would do dy, right? Opposite over hypotenuse, that's dx squared plus dy squared. Right, so that's sine theta. Is that clear? If I draw that angle theta, right? That's the same as dy by dx over 1 plus dy by dx squared. Right? That's what we have here. This is equal to, I can write this as the refractive index times a function which captures the sine of the angle in there. And that should be very familiar, Snell's law, right? But not yet Snell's law. It is, the features are sitting there. The characteristic of a Snell's law is sitting there. And that's where Fermat comes. Fermat says that this is a usual derivative, set this to 0. Fermat would set this to 0. So Fermat's theorem, so this is now all standard. Fermat's principle or Fermat's theorem, right? I don't know which one. Fermat's principle is that the variation in the time taken for light with respect to any, oh, this is x prime, by the way, sorry. Right. With respect to any trajectory is equal to 0. Right. So that means that the derivative prime of this particular construction, the product construction of refractive index and the sine of the angle is 0. If something's derivative of something is 0, you say that that's equal to a constant. And that's Snell's law. So this is Fermat's theorem. That's Fermat theorem. And this is Snell's law. Fermat theorem implies Snell's law. Right, that's just 3 sentences there, and that we use the machinery of functional derivative to get that. If it was just one interface, you would say this is n1 sin theta 1 is equal to n2 sin theta 2, but now we are saying this is valid at every turn that light takes. Like it's a continuously, it is keeping that constant. And I'll stop here. 5 minutes over. Good.